Good morning, everyone. My name is MOOI. I am an undergraduate final year student from University Technology Malaysia, specialized in Faculty Precision Mechanical Engineering. Today, I'm going to share with you about my final year project with title Implementation of Uncertainty Analysis of Thermocouple, supervised by Prof. Yutaka Asako. Before going into the title, I would like to introduce to you what is thermocouple, why we need to know the uncertainty analysis of thermocouple, why it is important. Okay, so thermocouple is a common and widely used device in many industrial, scientific, and OEM application. It is a temperature sensor to measure temperature. It can be found in nearly all industrial markets, for example, power generation, oil and gas, pharmaceutical, biotech, and so on. Thermocouples are typically selected because of their low cost, high temperature limit, wide temperature range, and durable nature. Therefore, reliability of thermocouple data is important for researchers to verify their research result. For temperature measurement involving thermocouple, uncertainty needs to be determined before deciding the reliability of data. Experiments that involve measurement and equipment that generate data, result obtained will never achieve the exact value of measurement due to uncertainty. There are plenty of ways researchers have tried to get the uncertainty of thermocouple by using other equipment, but for data loggers that involve thermocouple, uncertainty is being considered, but it is complicated as shown in Figure 1. Next is about the project background. In most of data logger used for temperature measurement by the thermocouple, the internal temperature near the reference junction terminals is measured for the reference junction compensation, which is the temperature difference between the internal temperature and the terminal temperature results in the reference junction compensation error. As what I have mentioned just now, previous way is complicated. So, the RJC error has been determined by measuring the terminal temperature and the internal temperature for each channel as shown in Figure 2. It takes time and effort to obtain this temperature of all channels. To obtain the uncertainty of the reference junction compensation, this measurement needs to be repeated many times. Therefore, an easier and faster way to obtain the reference junction compensation error is strongly required. Hence, a new, easier and faster way to obtain the reference junction compensation error is proposed in this research. This is a parallel connection as shown in Figure 3. The measuring principle of the reference junction compensation error is very simple. The measuring junction is put in the ice bath of 0 degrees Celsius. If there is no reference junction compensation error, which means 0 degrees Celsius, will be displayed in the data logger when the measuring junction is put in the ice bath. Therefore, the reference junction compensation error of each channel will be displayed when the measuring junction is put in the ice bath. The reference junction compensation error is obtained by putting the measuring junction in the ice bath. The proposed parallel connection has been tested in this research. Uncertainty value play an important value in ensuring user safety. Thus, thermocouple is chosen as temperature sensor to be used together with data logger. Then, come out with the research objective are to obtain uncertainty in concise and effective way. Second, uncertainty due to the instrument resolution, fluctuation, reference junction compensation, and thermocouple measurement. Okay, next I will talk about the methodology of this research. The thermocouple is connected to terminals of all channels. If the internal resistance of each channel is infinity, the voltage drop will not happen and the same electromotive force will be measured at all channels. However, the internal resistance of Hioki data logger is 1 mega ohm. The voltage drop channel by channel. To verify whether parallel connection could correctly measure the electromotive force of the thermocouple in each channel, the voltage of each channel is obtained by open modelica, as shown in above figure. The voltage of the rightmost input channel is 0.9999 volt when the input voltage which corresponds to the electromotive force of the thermocouple is 1 volt. The percentage error is 0.01%. Since the resolution of the data logger is 0.1%, the percentage error of 0.01% is small enough. Then, the parallel connection is established. After verification, the experiment is conducted. The effect of reference junction compensation will be determined by comparing temperature measured by thermocouple, which directly connected to data logger. In Hioki data logger, voltage measurement for a measurement range of negative 10 mV to positive 10 mV. The accuracy given in product specification is plus minus 10 mV. By conducting inverse polynomials, the resolution limit of data logger in temperature could be obtained. Next, experiment for random error was set up early in air conditioner room to ensure room temperature achieve constant and will not affect temperature of metal block. Data readings were taken after thermal equilibrium achieved. After get ready all the data, combine all the error source and it will be computing by root sum square. Next is about the uncertainty results. The uncertainty of the instrument consists of the resolution of a data logger, the accuracy of temperature measurement caused by the accuracy of the voltage measurement. Since the Hioki resolution is 0.01 degrees Celsius, based on the specification of the data logger, the uncertainty of the resolution is plus minus 0.005 degrees Celsius. Since the uncertainty of the resolution is much smaller than the uncertainty of temperature measurement, then the uncertainty of the instrument is equal to the uncertainty of temperature measurement, which is plus minus 0.26 degrees Celsius. The uncertainty of fluctuation was obtained by measuring temperature of a metal block under control surrounding temperature. The 50/60 frequency cutoff filter setting is selected. The uncertainty of the resolution is smaller than the fluctuation. The uncertainty of random fluctuation is not constant. It is much smaller than the uncertainty of the instrument and the uncertainty of the reference junction compensation. Then, the overall random error for T thermocouple is between plus minus 0.015 until plus minus 0.029. For the uncertainty of reference junction compensation, figure above have shown there are results of 5-second interval long 1 hour among 15 channels of data logger. Ice bath temperature is almost 0 degrees Celsius when the ice bath is filled with the shaved ice and water. So, the true temperature is 0 degrees Celsius. Therefore, the lowest temperature of each channel indicates the reference junction compensation error. The greatest difference obtained was negative 0.77 degrees Celsius occur in terminal 8. Hence, the error from reference junction compensation is negative 0.77 degrees Celsius because it has the lowest temperature. Overall uncertainty obtained with root sum square. The parameter of data is including uncertainty of instrument error, uncertainty of reference junction compensation error, and uncertainty of random error. In a nutshell, based on the simulation, parallel connection is established. Have shown that it is a better way to get uncertainty of reference junction compensation. Measured temperature by the Hioki data logger is plus minus 0.77 degrees Celsius for the thermocouple T when the RJC is used. The result is taken at every 5 seconds long 3600 seconds. Therefore, the value is more precise compared to previous research. Yes, that's all for my final year project presentation. Thank you for your listening. Thank you.